Hello. So, January the 30th, starting on problem 12. Oh, we can't write there. No. All right. Now, I have some new hardware. OBS was not at all satisfactory. The sound was bad and the video was hopeless. So, in the end, I started a new software, and as you probably saw in the beginning, it's called VocoScreen, and it's just an interface to Linux MPEG system, FFmpeg. So it seems to work quite efficiently, so I hope the quality will improve significantly. All right. Now, this is actually the second recording of the beginning of this problem. I recorded once with OBS. It's no more on the screen here. What is it called when you throw it away? I've purged it, so there's no trace left on it on the computer. Now, so I did this once with such poor quality that I decided OBS works no more for me. Well, and I was just beginning on B, so but I have to redo A, of course. Now, so we have two conditions. All the roots are real. And G2, G3 real, and the discriminant positive. We have to show a by implication here. So we assume EI are real. The first thing we can conclude is that the sums are real then, because they're symmetric polynomials in EI. Being the coefficients in this polynomial. Next, we have to show that discriminant is positive. I still have problems with the throat. Maybe you can hear the storm in the background, so it's still quite windy here in Denmark. Now, what do we have? There are three ways to go about it I know of. The one is trying to solve the equation that this vanishes, and there are two ways to do that. One is Cardano's original idea, writing x, the solution as the sum of two variables. The second one is writing it as sine to 3 times an angle, and then using the addition formulas, the trigonometric addition formulas. Now, I would try another way, and that's we define this function, we use real function theory as a real function. And by and large, it goes like 4z to the third. That really looks like a number 2. So, in order that it can have 3 roots, we must have two places with horizontal tangents, and the values there must be negative. So we solve the derivative vanishes, It's actually symmetric, all right? So let's compute the values of these 2 points. And I find it very useful to put z outside the parentheses here. For z squared minus d2 minus d3. So 4z squared, that's a third d2. So, didn't I say a third? So that's 4/3 minus 3/3, that's 1/3. So plus minus, so that's a half times d2 third and 3/2 minus d3. And these two values must have opposite sign. That means that the product is negative. If we use minus first, and then the plus, that's the sum times the difference. So it's minus this guy squared minus this guy squared and that must be negative. Oh, that's the minus, so it becomes plus here. That should be negative. So we change sign and let's just do it. D2 to the third minus 4 times 27 d3 squared being positive. So we compare with what we should have got, and as you can see there's a factor 4 amiss here. Well, it's probably from here it goes wrong. So let's just check it once there. So this was z times 4, z to the third, and z to the third, or z to the second, that's a 12th d2, and 4 divided by 12, that gives like so it seems that 4 was just a blunder. So 4 divided by 12 gives a third. Let's see if we can correct it. We do away with this 4. We do away with this 1/2. We just have to do it again then. Oh, we have to do this as we do away with the 4. And then it's minus 2/3. Here, minus 2/3 d2 plus minus 2/3, and that takes the factor 4 from under the square root, meaning this vanishes, and then this, surprisingly, the signs become, well, they change signs of course, but it's the same 2 we end up with. And that means that this half is gone. So this one is gone, and this one is gone. So we do get the discriminant here. All right. So that was from the left to the right. So maybe we have just space for it down here. Assuming G2 and D3 is real, and the discriminant is positive, then it seems it's easy to go backwards. So we need to show that the derivative has 2 roots, and then this condition is that the values are distinct where the tangents are horizontal. So all we need to show is that this equation has 2 solutions, and that just requires G2 positive. So will G2 be, that must be a consequence of the discriminant being positive, and that's exactly the point here. So that was my mother-in-law on the phone. Now this system has the advantage that I can pause it, so everything is very nice. So that was 12a. Going to 12b. Now we can. This integral makes sense, of course. We just have to put E1, E3, so that's our roots on the real axis. So this integral makes sense. This integral makes sense. So, and it will give minus, we have that from problem 11, it will give minus a stationary point of the Weierstrass P function. And of course, since this is real, it will give a real point. So that's the first one. Now the next one, that's where we go from E1 backwards. So the stuff under the square root will be negative. So we change its sign, and then we get I down here. And that gives a minus I up here. So we change the direction of integration. Wasn't that what they did? Exactly. So it gives a purely imaginary and now I forget the word. It's an original point. Let's call it omega 1. So that P of omega 1 equals half of omega 1 equals E1. So that tells us something about the lattice that we are dealing with. So if we have the complex plane, then we have points etc. Now this need not be the whole lattice, and the guy we get here, the guys we get from these integrals need not be the first ones. But now if we the problem here is that there may be some points in the lattice in between. The lattice may be generated by say omega 2 and this guy and not this guy. So I have to find a way to do away with that. So we have to show that L is generated by these So can we do it by taking some paths, some different paths, and investigating them? This is a maximum, so if we integrate backwards, we subtract something, and then it's subtracted again, so it becomes less. And this way it becomes larger. This is not at all obvious to me, and I feel a little pressurized now to get ideas online. It's difficult, and maybe I'll get more used to it later on. And then I do have a lunch appointment, so I need to be going in half an hour, even before in 20 minutes. So I feel like the brain has stopped here. I did get one idea, but it didn't bring me anywhere near. So I'll just make a break here, and then I'll return when I have an idea and see if that will work. So, welcome back. I have an idea. We just need to remove this picture. Okay. There we go. Now, this is the formula 6.2, the series expansion of the Weierstrass P function. I did that in the first recording without sound, so I'll just show you my thoughts. G2 and G3 are real, so capital G4 and 6 are real, and all the coefficients here are integers, so G8, 10, 12, etc. all turn out to be rational. That means that we have a real expansion of the Weierstrass P function, and that's very nice. So if we go in along this line, all the values are real, so we are integrating on the real line out here. So that means that this is really omega 2. And if we go in here along the imaginary axis, because it's all square, it's g to the 4th, of course, here. Oh, that's where I just have to check the formula. Yeah, I was right, g to the 4th. It will all be real as well, so going in here, and then z squared, I squared is -1, so we go towards minus infinity. So that means that going in here equals the integral from here to minus infinity. So this is really omega 1. So we need to show that any guy in the lattice, any point in the lattice, will be an integral, or be in the lattice generated by omega 1 and omega 2. So we take any one here, and then we shall show that this guy can be expressed in terms of omega 1 and 2 using only integers. And let's use this path. Where t goes from the modular of omega down towards naught. So we have to show that it will generate a path whose integral can be expressed in terms of omega 1 and omega 2. Now, how it tends towards infinity we can actually see because of this expansion. The leading term is 1 divided by z squared. That should be 2. So that means that going twice the angle, that turns out to be something like down here. Like there. Never mind. So that should be the asymptote of of the values going out here. So it practically goes towards infinity along a red line. So it may come from E3, but it may come from anywhere else. Now if we call that, that's bad color. If we call that omega, and then the Weierstrass P of omega, so that will be some curve. We don't know how it goes, but it will end out going in this direction. So it might go something like this, and then going out in that direction towards infinity. That doesn't really prove it, what I wanted to prove. So we have to think a slightly different way. We know from exercise 11 that all the pre-images come by varying the path. So we have to show that all different paths give differences by omega 1 and omega 2. That means that the lattice must be generated by then. That means we'll have to know the integrals from E1 to E3 and E3 to E2. So that raises the question, and from E2 to E3. And this is where I actually got an idea. We'll just put the this guy on top. There we go. This is where I got the idea to handle that problem. And the point was to integrate like this. Out to some large radius r. This integral say starting here, going around. Vanishes. And the integral along the large half circle will tend to 0, tend to naught, because we already did that earlier. That means that choosing the what's it called, the branch of the square root correctly, then the integral, oh, it should have been black. The integral from minus infinity to infinity of 1 divided by the square root dt should vanish. Now, we choose plus here. Then when we go around here, we change it by pi, and what's it called? The argument is raised by pi. So if we go like this, it's raised by pi. So this one is, we subtract half a pi. So that means it's minus I times the square root of the absolute value. Here we divide here we're going to circle around, so let's just change the sign. And then when we come out here, it's plus I. So that means that this integral equals E3 my idea was that these two are imaginary. And these two are real. So they must be equal, pairwise equal. So I claim that the integral from minus infinity to E1 equals the integral, what am I doing? I don't know how I managed to do that. From E3 to E2. And the integral from E1 to E3 equals the integral from E2 to infinity. Now, we'll just have to check this using Mabel. I see that this guy is not working, so what's going on here? Well, we'll just take it away, a still picture here. Or maybe we should open it again. I like to have it that you can see that I'm actually there doing something. Oh, it's busy. Device is busy. So, okay, I've used it. So we'll just check it on Mabel. Oh, it should have been 1 divided by square root. And then I forget, we are actually in Maple. There we go. And then let's see if we can't do the integral. It might be possible from -1 to 0. That's strange. It should know what f of x is. It doesn't. Oh. There we go. Indeed, it knows about elliptic k, all right, and then from 2 to infinity. So they do agree, so I was right. I had actually imagined that I needed to do numeric integrals to verify this. So lovely. So this integral equals a half omega 2, and this I'll just have to check exactly what that was. Minus I. Oh, no. This integral is imaginary in itself, so that was because they changed it. So it is actually half omega. We go from E1, yeah. So, oh yeah, and this, yeah, never mind about the signs. So that means that any curve going around say if we, let's go back to this guy. If we start up here and then tend to infinity directly, we get one value. And if we go around this one and then out, then it's like going down here, this way, out, up here, and then out. So that means that we are going this way, that's subtracting omega 2 and then adding, no, omega 1 and half an omega 1, then adding half an omega 1. So this way, here we are minus, and we are going that way, so it's plus half omega 1, and then plus another half omega 1, so it's plus omega 1, and then out to infinity to get the same result. And if we go round around these two, it's omega 1. So we need to find out what happens if we go around both of them. So we go around this one, back here, then around this one. That's what we need. So well, it will of course be some integral having some integer, omega 1 and omega 2 with some integer. We just have to check it. We need to check it. So this is the path. And if we start here with that being plus, then we go around pi. So that's e to 1/2 pi I. So that's one imaginary unit. Going back here changes sign. And this is another factor I, so that becomes a minus. And since we're going backwards, it's twice the integral from E1 to E3, and then we get the imaginary integral here, which is twice that one, so it actually gives. And that was omega 1 here. Right. So I believe now that I have reasoned myself up to a point that all the pre-images will be generated by paths around the roots here, and all those possible paths, they give pre-images that vary by integer times omega 1 and omega 2. So that means that the lattice can be generated by omega 1 and omega 2. And in particular this one, this guy, if it was, say, like this, then all the pre-images of that that's the worst example to choose, because if it is in the lattice, then it's infinity. The integral is infinity, and this integral is obviously finite, isn't it? Oh, the integral doesn't give us the Weierstrass P function. I thought I would be making my argument very clear here, and then it turns out that no, it was not clear. All right, leave it at that. Now, the last question, C, we need to be very specific. So we have a value of Z, and then we need to get all the other pre-images. Well, that's not so difficult when we have this in place. If we have u equals the Weierstrass function of z, then to get one path that gives u, we use the trick defining the path like this. This should be the one. It has to avoid the roots, of course. Oh, but they are real, so I would like to, if it's real, then well, then we just choose another set. Never mind. So let's have a path giving z. The next thing is to say, now if we have another set, that's called set naught. If we have another set find the path. And omega 1 comes from going around E3 and E2. So So we go around here. That was n times up to u. And next, or before, we go around here m times must be green. And then we get this guy. And to get the negative, we just have to go around one of the roots once, and it doesn't matter which. So, I believe that this solves the problem. And now we can actually see the end, having only two problems left, although 14 has 4 questions, but I can see the end now. This has been a very hard section, and I've learned a lot, I must say. After reading section 7, I couldn't help thinking about exercise 12 of section 6, and I do believe that I made some false claims. I've been thinking a little about it, so this is not working on the problem, but rather a presentation of what I've found out. We have here the 3 real roots of the content of the denominator, a number u, and integrating along a path towards infinity, we get the value z, so that the Weierstrass p function, oh my god, that's so clear. The Weierstrass p function of z equals u. Now, I made the claim that taking a path towards infinity, circling around u1, and then going towards infinity, would change sign of u, and I think that's wrong. So let's try to look at it. And the way we do it is that we are going down towards e1, then making a small circle of radius r around it, and then going towards infinity. And the way to go towards infinity is we go down to the negative real axis, once around one circle of radius r, and then towards minus infinity. So let's try to do it explicitly. What will the result be of integrating along that path? First, let's say that we wind down to the negative, the branch where the square root is, it's imaginary, so that the square root is minus I. It could be plus as well, so let's take both of them anyway. So we have that the integral from e1 to minus infinity, I won't write the content here, equals minus plus 1/2 omega 1, which is purely imaginary. So, going this way out towards infinity, we get the same value. So if we go over u further on towards infinity, it's still minus plus 1/2 omega 1. Now, this part of the integral gives z, and that means that the integral from e1 to u must give minus plus 1/2 omega 1 minus z. So the integral from u to e1 equals z plus minus 1/2 omega 1. So that was going from here. And now if we go straight away to infinity along the negative x-axis, we will of course get z back by adding this to this. But if we go once around, Then we come around to the opposite branch, so the sign of this one will be minus or plus. And that means that the integral from E1 going out along this branch, is the opposite of this one. And therefore the path from U around towards infinity gives this plus this z plus minus omega 1. As far as I remember, I claimed that it would change sign on z, and from this calculation, if I'm right, it actually adds omega 1 to it. And going twice around, then we come to the original branch, so there the integral going twice around will give the original z value again. So we have to do it very explicitly in order to find out what happens. So let's look at the question 12b. So we have a lattice given by U1 and U2, where it turns out that all the roots are real. Then we have the two values, omega 1 and omega 2, given by these two integrals of 12b. They lie on the z-axis, somewhere on the real axis and on the imaginary axis. And were defined, of course, so that the imaginary value was positive and the real value here was positive. Now, that means we have a lattice point lying on the axis. There is a smallest lattice point on the real axis then. Let's call that omega. And of course I want to show that this is actually omega 2, and I don't think that I made a good case for that in my work on the problem. So I'll give you an idea which I think works. Now, what I mentioned was that we have a series expansion around 0 that will work in a certain, it has a certain radius of convergence. And then I wanted to make analytic continuation out until omega, showing that it had a path along the real axis. So in the first part, within the first radius of convergence, in this case it's the modulus of U2. Within this radius we know that the values are real from the series expansion. So how can we extend that out to omega? And that's by analytic continuation. But how can we continue outside this region of convergence? And there is a band around the real axis up to omega without any other lattice point. And a little further, by the way. So let it have a size d. So half the width is d. And that's because the area of the parallelogram spanned by two members either vanishes or is a multipler of an integral multipler of the area of this parallelogram. No, you can't see it. Of the one spanned by U1 and U2. So we can go in d quarter, d8 before this, and then d quarter here before that one, and then analytic continuation. All the derivatives will be real, so the series expansion will have real coefficients. And that means that the radius of convergence is larger than or equal to d. So we can go out here d half, d quarter before. So we'll get d half further anytime. So each time. So in a finite number of steps we will reach omega. And this means that omega comes from an integral from plus infinity down to E2. And that means that it must be the omega 2. So that should be my proof that the smallest omega on the real axis is actually omega 2. So next we have to show that omega 1 and omega 2 actually span the entire lattice. Now I come to think of it, we don't need this at all. So let's have a set that comes from integrating from a certain u, where in the other space where we have the roots here, where our paths run. So some path tending to infinity will give set. Then we take set plus u1, any of them, and then we want to find a way to get this, a path to get this. That's very easy. We had that in problem 11. That's just taking a path going from set to 0, and then we'll get a path that actually gives this guy. So we know such a path exists. And they have the same values, of course. It's a lattice point. Oops. So using U here maybe was not the brightest one. Well, it works. So, so there is a path that gives this. So the point is that I want to show that all the possible paths from U towards infinity will give Z plus an integral number times omega 1 and an integral number of omega 2. If I can do that, then I will have written U1 as a linear combination of omega 1 and omega 2. Now, and here I've shown how we can actually try to do the different stuff. Now let's apply this. So the idea is we need to know when we go towards infinity from E1, what can the result be when we integrate towards infinity, any region, any path here. So I had to think a little about what does the family of paths look like really. So what is the topology of our space? So that means C minus E1, E2, E3. What is the topology of it? And that's of course the family of curves. So we have an algebraic topology. As I see it, we can visualize this space as two intersecting tubes, the surface of the tubes. And I think that the homotopy group is generated by rotation around three of the tubes going out. So we can use going around E1, going around E2, going around E3 and E2. Now that's because going around, once going around E1, then E3, adding those, you get this. Add with one going around here, then you get one going around it all. And that's just one going around infinity. Although it's also going around all the three others. So I stated, I think, in the original video, that whichever direction we go towards infinity, that or that, and then upwards, it would get the same result at the end. But I think I also made the claim that it would change sign, so which is true. And to do that, we have to do it in great detail, and I'll try just to do it down here so to get the idea of what we are dealing with. Now, we've come down to E1, and to be specific, let's assume it's minus I here. Then when we go around here, and then go up to E3 around here, up to E2 around here, and then backwards above the real axis, and then letting it. That, of course, we do it on the real axis. I just draw it above to show that we are on another branch, so it's not confusing. So we have to write which branches are we on. This is real, so times I, that gives plus 1, plus I, round, minus I, times I, that's plus 1. So actually going around 2 of the units here, then we come back to the original sign. And then we end up on plus I. So the integral here from E1 to E3 gives half omega 2. This is plus gives a half omega 1. Round, going back here, minus gives plus omega that's omega 1, and then minus omega 2, and then we are back here going out, so we'll have to write it, what it all gives. This was the first one here. I'll just do it up here. Or rather, first we go down to the to E1. We have that here going down to E1, and we need to have the plus sign. Do we not? It's minus I we go down to. So it's I just have to do this again. So we go down to the negative, so that the integral from E1 to infinity is plus. So we have to choose the lower sign. So it's set minus a half omega 1. That was from set down to E1. Then we go to E3, that's plus 1/2 omega 2, plus 1/2 omega 1, around here, and then plus half omega 1, minus half omega 2, and then we go from here out. Oh my God, I've made the wrong sign here. So, no, that's the plus, and that means that the way out gives minus 1 omega 1. So let's see what happens. All of this set we do have. And then minus omega 1, plus omega 1, plus omega 1, minus omega 1, cancel. Half omega 2, minus half omega 2, cancel. So, going all the way around, all three zeros, going once around infinity, doesn't change the result. So the first claim I think I made, which was that going towards infinity at a different angle, even if you change it by 85 pi, doesn't change the result. Now, the point is that we have to find out what are the possible values of going to infinity from E1, E3, and E2. And I just want to make the claim that the integral from E1 to infinity may give any of these values where m and n are arbitrary integers. To solve problem 12b, we just have to show that it's integers. It's in C, we have to show that it can be done. We can arrange that any integer occurs. And the same with E2 and E3 analogously. Now, I think this is very easy to see. When we start out, then the direct way going from E1 to infinity is gives m equals naught. So if we go via E3, then either branch will add half omega 2. And then when we go to E3, we can have any of these, and adding half omega 2 to any of these give the one we come from. And the same, this is half omega 1, we have to add or subtract, and therefore coming from them. So you can see how we could go around, and so this is really all the possibilities going around E1, E3, E2, any way we want. We'll still end up in one of these. And that means when we add this to our U, so first we go from U to E1, and then we go from E1 to U. Now, depending on the path, the first one was Z plus minus half omega 1. And the second integral here from what did I do here? That should of course have been from E1 to infinity. So now that one looked right. We've seen that many times. Plus, and E1 to infinity, we have that up here. So this is, if it's minus, they cancel. If it's plus, we change m. So this means that any path will give the original value plus a member of the lattice spanned by omega 1 and omega 2, and that shows that the original ones here are actually spanned by omega 1 and omega 2. So I think that by now I have solved problem 12b. And if any details were missing in problem 12c, I hope you can make them very easily from the work I've done here. So that was it. And as you can see, it's today the February the 9th. So weeks have gone by. I've been very busy handling family matters. It's been a hard time, but I hope that I can get some more problems solved pretty soon.